Alright guys, let's start with our first theorem. If a sequence Pn converges, then it has a unique limit. Unique limit means it does not have more than one limit. Alright, in other words, it can also be stated as, let Pn be a sequence in a metric space X if P belongs to X and P dash belongs to X, and if Pn converges to P and P dash, then P is equal to P dash. That means here your sequence Pn is converging to P and it is also converging to P dash. So we have to prove that these 2 points are equal because limit should be unique, right? So let's start with the proof. We are having the sequence Pn, so let Pn be a sequence in a metric space. I'm writing MS for metric space X such that this Pn is converging to P and it is also converging to P dash, since it is given that our sequence is converging, where P and P dash both belonging to your metric space. Now, what is the definition for convergence? Whenever sequence Pn converges to a point, then there exists, for given epsilon positive, there exists an integer n, alright, for which the distance between the sequence and the point, the terms of the sequence and the point, that distance should be strictly less than epsilon. So because sequence is converging to 2 points P and P dash, so I am writing, then for given epsilon positive, there exist positive integers n1 for P and one more integer for P dash, n2, such that distance for Pn to P, this is less than epsilon, but I am taking epsilon by 2 since your epsilon is very small positive real number. For n greater than equal to n1, and also distance of Pn to P dash is also, I'm taking less than epsilon by 2 for n greater than equal to n2. Now what I have to do is, I will take this maximum for these two positive integer, right? I'm taking n to be the maximum of this n1 and n2, and then write the result again. So put n is equal to maximum of n1, n2. Then distance for Pn, P is less than epsilon by 2 for n greater than equal to n. I'm taking now the maximum one, n. Suppose you are having n1 to be equal to 2, n2 equal to 3. If you take the maximum for these two, suppose the maximum will be 3, then the result, both the results holds true. See, suppose this n1 is 2 and this n2 is 3. Suppose, let us assume that. So what is the maximum for 2 and 3? What is the maximum for 2 and 3? This will be 3, alright. Now the result, second result holds for n greater than equal to 3. If the first result holds for n greater than equal to 2, then it can also be true for n greater than equal to 3. Because n greater than equal to 2 means the result is true for either n strictly greater than 2 or is equal to 2. Both the ways, right? So if it is true for n greater than equal to 2, then it is also true for n greater than equal to 3. N strictly greater than 3, because we are taking the number n equal to 3. So both the results holds for the maximum of n1 and n2. So just take only the one positive integer for both the results. And distance for Pn and P dash is also strictly less than epsilon by 2 for n greater than equal to n. This is the definition for convergence. Now we have to prove that P equal to P dash. So let's check the distance for P and P dash. This will be less than equal to distance for P, Pn plus the distance for Pn and P dash. Can I write like this? This is your result, that distance between the 2 points is less than equal to distance between P and Pn plus distance between Pn and P dash, right? If you are having P and P dash, then the starting point and the ending point should be these two only, and you take the in between Pn, all right? So what is this distance for P and P dash? This is less than epsilon by 2 from here. So this is strictly less than epsilon by 2, and plus distance for Pn and P dash, this is also strictly less than epsilon by 2, which comes out to be equal to epsilon. Alright, this implies distance for P and P dash is strictly less than epsilon. Okay, but epsilon was arbitrary. You can take epsilon to be as 0.0001 or 0.00001. It is just epsilon is your strictly greater than 0, a positive real number. You can set any epsilon. So because epsilon was arbitrary, so the distance is tending to nearly 0.000. That is, the distance between these 2 points is just approximately equal to 0. So here we can say that P is equal to P dash, right? Hence the sequence. So these are to the points where the sequence converges. So that means where the sequence converge, nothing but only at the unique limit. So thus the sequence Pn converges to a unique limit, right? Okay, all right. Next, another theorem is there. If a sequence Pn converges, then it is bounded but not conversely. Now just now we have done that if the sequence Pn converges, then it is converging to a unique limit. The other result, if a sequence Pn converges, then it is bounded. That means convergence implies boundedness. But converse need not be true. Boundedness does not imply, may or may not imply convergence. But convergence definitely imply boundedness. So let's go for the one way. If a sequence Pn converges, then it is bounded. We have to prove that it is given that sequence converges, then we have to prove that it is bounded. Before that, here a note is given for the definition for the boundedness in the metric space. Let X be a metric space and let Pn be a sequence in X, then Pn is bounded if there exists P belonging to X and a number K such that D of Pn and P should be less than equal to K for all n belonging to N. This is the definition for the boundedness. If we got this result, we can say that our sequence is bounded. So it is given that Pn is convergent sequence. So let Pn be a sequence such that Pn is converging to P. Alright, whenever the sequence converges, then for epsilon I'm taking this to be equal to 1. There exists a positive integer, let's say n, such that distance for Pn and P is strictly less than 1 for all n greater than equal to n. This is the definition for the convergence. Now see, your distance, suppose Pn sequence is having the terms P1, P2, P3, P4, so on. Alright, and this is your point P where the sequence is converging. Alright, now we are saying that distance between the terms and the point P is strictly less than 1. So we don't know how much distance they can be taken. So let's suppose that alpha to be as the maximum distance for P1P, P2P. We have taken all the distances, and let's say alpha to be the maximum of all these distances. Alright, so if alpha is the maximum distance, what does 1 imply? This 1 is either strictly less than alpha, because alpha is the maximum distance and we know that this distance is strictly less than 1. So either 1 is strictly less than alpha or it is equal to alpha. Okay, two cases are there. Either 1 can be taken as strictly less than alpha or it is equal to alpha, because alpha is a maximum distance. So we take alpha to be as a maximum distance and write the result again. So let alpha is equal to maximum of 1 d P1P d P2P d P3P and so on. So then distance for P and P, which is strictly less than 1, I'm now writing that this distance is less than equal to alpha for all n belonging to n. Is it clear? Alright. Now see the definition again in the note. We have got this result. So from here we can say that our sequence is bounded. So the sequence Pn is bounded. Proved? Alright. Now the other way, conversely. Converse says that a bounded sequence may not be convergent. So let's find one bounded sequence. Can I consider this sequence? Take the sequence as -1 to the power n, where n is the natural number. Alright. Now see, what is the sequence is this? What are the terms you are getting? For n equal to 1, we have -1. For n equal to 2, we have 1, and then again -1, then 1, again -1 and 1, so on. Is this sequence bounded? Yes, because it has lower bound as -1 and upper bound has 1. Alright, this is a bounded sequence. It has lower bound as -1 and upper bound as 1. So it is bounded between the 2 points -1 and 1. But is it convergent? For convergent sequence, we need a unique limit point. How many limit points are there in the sequence? What is the definition for the limit point of the sequence? What is the range of the sequence? the distinct points, right? So this sequence is converging to -1, and also it is converging to +1. So we have two limit points over here, -1 and +1. So the limit point is not unique in this type of sequence. Hence, we can say that this bounded sequence is not convergent. Clearly, it is bounded, but not convergent. Right? So what we got the result? Convergent implies boundedness, but reverse case need not be true. So convergent implies boundedness, but the other way need not be true. So here ends up the result, two results we have done. In the next video, two more results we are to discuss. Thank you for watching this video. Enjoy your day.